Hello everyone, my name is Dan Bing from Fondazione Bruno Castellani, Italy. The title of my presentation is Estimating Logarithmic and Exponential Functions to Track Network Traffic Entropy in P4. The co-authors are Marco Salvi and Domenico Siragusa. Let's start with network monitoring and security functionalities. In OpenFlow-based software-defined networks, the monitoring and security tasks are usually executed in a centralized controller. This comes with two drawbacks. The interaction between the controller and the switches may generate significant communication overhead, also high latency. Now, with the advent of data plane programmable switches, by using P4 language, the tasks can be partially or fully executed in the programmable switches. Such tasks include heavy hitter detection, flow cardinality estimation, DDoS detection, and also network traffic entropy estimation. In this paper, we will focus on network traffic entropy estimation. The network traffic entropy usually relies on channel entropy, and it indicates the traffic distribution across the network, which means that when all parties belong to the same flow, the traffic entropy is zero. When all flows are uniform distributed, it reaches the maximum. So a periodical track of entropy helps diagnose security and performance issues. For instance, to detect the DDoS attacks, when a DDoS attack happens, the entropy of destination IP significantly decreases. Likewise, for the polar scan detection, the entropy of destination IP and destination port significantly decreases. Now the question is it implementable in P4-enabled programmable switches? P4 is a well-known and commonly used high-level domain-specific language for programmable switches. It supports a sequence of arithmetic and logical operations. However, like logarithmic function, exponential function, loops, division, and floating numbers, all of them are not supported. So the goal of our paper is to enable logarithmic and exponential function estimation as the building blocks for network traffic entropy estimation entirely in P4. Why do we need the logarithmic and exponential function estimations? First, we see the channel entropy formula can be rewritten to a simplified formula, which means that this simplified formula can be computed by using 3 times of logarithmic computation and 1 time of exponential function computation. There is a state-of-the-art in programmable data plane needs thousands of table entries in TCOM for the logarithmic and exponential function estimations to assure the relative error is under 1%. However, we know that the TCOM is expensive and power hungry, so also the state-of-the-art needs a controller to populate the TCOM lookup tables in the switch. And the network traffic entropy estimation should avoid using TCOM to work entirely in programmable data planes. Our contributions. We first propose the P4log for the estimation of logarithmic function and P4x for the estimation of exponential function. Then based on these two algorithms, we propose P4 entropy to estimate the network traffic entropy without relying on TCOM. Finally, we implemented the prototypes of the proposed algorithms and strategy in the P4 behavior model, proving that they can be entirely executed in the programmable data plane. This is our P4 log algorithm. The input is an r-bit integer x and a given logarithmic base d, and the output is the estimation of log dx left shift 10 bits, which means that the log dx is amplified to power 10 times. This is because the floating number in P4 language will be truncated to only the integer part. So if we amplify the floating number, we can compute it in P4 language. So first we have log dx. We decompose it to log 2x times log d2, and then the log d2 is a constant which can be computed and preloaded in the switch. Then we decompose the log 2x into integer part and decimal part. In the integer part, we can calculate it by taking the index of leftmost one of x in binary value. Then we see that the decimal value is a constant, but in P4 we have to use several bits to estimate it. We call it n bits, and the result of the decimal part, we also need to consider the number of digits after 0. So this constant can be pre-computed by using binary search tree, and we see that the accuracy of P4 log depends on the estimation of the decimal part. This is our P4X algorithm. The input is an integer base x and a real number exponent d. The output is the estimation of x power d. Similarly, we rewrite the x power d to 2 power d log 2x. Then the exponent d log 2x can be decomposed to the integer part and the decimal part. The integer part exponent can be easily calculated by using left shift. Then the decimal part, according to the binomial series expansion, the decimal part can be easily computed. We see that the accuracy of this decimal part depends on the number of terms in binomial series expansion. So based on these two algorithms, we propose our P4 entropy strategy. So first we have a packet stream S and a programmable switch. Now let's see how programmable switch estimates the entropy. First, we start a new time interval, and for each incoming packets, we identified it by flow key source IP and destination IP. But the flow key can be any subset of 5 tuple without any loss of generality. Then the counter in the switch +1. We then pass the packet to a sketch. Sketch is a memory-efficient data structure to store and estimate the packet count. It is composed by nh hash functions with output size ns. The accuracy of estimated packet count increases as nh or ns increases. Then we pass the estimated packet count from the sketch to some part. In some part, the pocket count fi times log 2I minus the previous pocket count estimated in the sum. However, in our case, by applying the L'Hopital's rule, the sum can be computed by using only one time of logarithmic estimation for each pocket. Then at the end of time interval, we can estimate the entropy by using the formula that we modified. We see that only at the end of time interval, we need to use 3 times of P4 log and 1 time of P4 exp to estimate the entropy. Finally, we report the estimated entropy to the controller. So we can say that P4 entropy can estimate network traffic entropy entirely in the switch. Evaluation settings. We consider relative error as the key metric for the evaluation for both algorithms and strategy. Note that for P4 entropy, we used a real flow trace and divided into 10 observation windows, each composed by 2 power 21 pockets. We used a fixed number of pockets for the evaluation, since the state-of-the-art only supports such an observation window. But our P4 entropy also supports the time interval-based observation window. This is the result of P4 log. So let me first recall the n bits and n digits. So for n bits is the number of bits used to estimate the decimal part, and n digits is the number of digits after 0 for the decimal result. Then for the testing values, we know that for 2 power L minus 1, it comes all ones for the input value. So it means that this will cause the largest bias for the decimal part for the estimation. So all bits after n bits are ignored and considered as 0. The algorithm leads to the worst case estimation when most significant bits after n bits are ones. We also have an average in this case. Average is the average relative error in logarithm estimations among randomly selected 5 power times 10 power 6 integer numbers such that x belongs to 64 bits. Now let's look at the figure A. In figure A, we see that if we fix the n digits to 3, when n bits equals to 4, the relative error for all cases are below 1%. Instead, if we fix the n bits to 4, in all cases, the relative error is always below 1%. It means that the relative error is not so sensitive to n digits. So a brief conclusion for P4 log is the relative error below 1% when n bits equal to 4 and n digits equal to 3. This is the result of P4 exp. We first fix the integer exponent d to a chosen value, then we find the largest 64 bits. integer base x that maximize the output x power d within 64 bits. Similarly, we also have an average value that is the average relative error in exponential function estimation among 5 power 10 power 6 integer numbers with base x belong to 32 bits and the exponent d belongs to 2 to 32, both randomly chosen. In figure A, we fix the n digits to 3 and n term to 7, and to vary the n bits. We see that when n bits reaches 7, the relative error is below 1%. In figure B, n digits is still not very sensitive to relative error. In all cases are below 1%. In figure C, we vary the n terms. We see that there are fluctuations in the figure. This is because we only consider the decimal number for the binomial series expansion. So some terms in binomial series expansion may be negative. This is why there are the fluctuations in the figure. And we see that when n terms equal to 7, all the relative errors are below 1%. So we conclude that the relative error below 1% when n bits equal to 7, n digits equals 3, and n terms equal to 7. This is the result of P4 entropy. Here we see that we implemented both our P4 entropy strategy and a state of the art. Here we call it the SOTA entropy strategy. We implemented both of them with count mean sketch and count sketch. We see that in both cases, the entropy strategies with count mean sketch always have much higher relative error than the count sketch. This is because the network traffic entropy estimation is more sensitive to the overestimation caused by count mean sketch with respect to count sketch. Then we compare the P4 entropy with SOTA entropy with only in case with count sketch. We see that if we fix the output size to 1000 in the sketch, when NH reaches 10, both of them, the relative error is below 3%. Likewise, if we fix the NH to 10, when the output size of hash function is 1000, both of them has relative error below 3%. Note that 3% is the maximum possible relative error, ensuring that accuracy of practical monitoring applications is not affected. Conclusion and future work. We presented two new algorithms, P4log and P4x, providing the estimation of logarithm and exponential function in P4. Based on these two algorithms, we also proposed the P4 entropy strategy to estimate the network traffic entropy. The algorithms have the similar accuracy to the state-of-the-art solutions, but do not rely on expensive and energy-hungry teacup while working entirely in the switch. P4 entropy adopts a time interval-based observation window that may allow the controller to synchronize the entropy connected from all switches. As future work, we plan to implement network traffic entropy-based DDoS detection entirely in programmable data planes. We also would like to test proposed algorithms and strategies on a real test bed. Thank you for your attention. Do you have questions?